Tonight, we're going to talk about the fact that the night sky is not a live broadcast, and that some of the things in it may have already killed us. Go outside on a clear night and look up. It feels like looking at something. A view. A place that exists right now, in the same moment you're standing there. It isn't. Every point of light in that sky is old. Some of it is minutes old. Some of it is thousands of years old. The light from the faintest smudges is older than the Earth. What you are looking at is not a scene. It's a stack of photographs taken at wildly different times, pasted into a single frame, and handed to you as though it were happening now. And that would just be a curiosity, except for one thing. If the news travels at the speed of light, then so does the danger, which means there is a category of event out there that, if it has already happened, has already decided what happens to us, and there is no possible way for you to know. Not because our telescopes aren't good enough, because the information hasn't arrived, and it cannot arrive early. But here's the question almost nobody asks. Not whether any of that is likely. How much warning would you actually get? Because that number is different for every threat in the sky. And once you line them up in order, something uncomfortable happens. The number keeps getting smaller. It goes from minutes to hours to none at all. And then, twice tonight, it goes negative because the thing had already passed us before anyone found out it existed. By the end of tonight, you will understand exactly how much notice each of these gives you, why some of them physically cannot give you any, and what the finite speed of light does to the word now. That last one is the real payload, and it is stranger than any of the disasters. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with a simple question. Where is the sun right now? You know where it looks like it is. On a clear afternoon you can point at it, but the light you're pointing at left the Sunday 8 minutes and 20 seconds ago, and in that time the Earth has moved about 9,000 miles along its orbit. So the sun is not where you're pointing. You're pointing at where it was, and the difference is real, and astronomers have to correct for it every single day. This is the first stage, and it's the gentlest one. Call it the 8-minute rule. The sun sits about 93 million miles away. That number gets said so often that it stopped meaning anything, so let's cash it out. If you could drive there at highway speed, 60 miles an hour, without stopping for fuel or sleep, the trip would take you about 177 years. You would need to have set off before the American Civil War to be arriving about now. Light covers that distance in the time it takes to boil a kettle. That's the thing worth holding on to. Light is not fast in the way a bullet is fast. It's fast in a way that makes 93 million miles feel like nothing. And yet, even at that speed, the sun you see is always a little out of date. Now, how do we know that? Because this is one of those facts that sounds like it must have come from a laboratory, and it didn't. It came from a man watching a moon of Jupiter go dark. In 1676, a Danish astronomer named Oumuamua was working at the Royal Observatory in Paris, and he had a tedious job. He was timing the eclipses of Io, the innermost of Jupiter's large moons. Io swings behind Jupiter and disappears, then reappears, on a schedule so regular that it was seen as a possible clock. If you were on a ship and you could see Jupiter, and you knew what time an eclipse was supposed to happen in Paris, you could work out your longitude. That was the practical prize, and it was worth a great deal of money. The trouble was that the clock kept losing time. Not randomly, that's the part that mattered. The eclipses ran late when the Earth was on the far side of its orbit from Jupiter, and early when the Earth was on the near side, and the pattern repeated with the year. Everyone else treated this as an error to be corrected. Roma treated it as a measurement. His reasoning was simple enough to explain in one sentence. The eclipses are not actually late. The light announcing them has further to travel, so it arrives later. In September of 1676, he made a prediction, in public, in front of colleagues who mostly disagreed with him. He said the eclipse due on November 9th would happen about 10 minutes later than the table said. On November 9th, it did. His boss, Giovanni Cassini, one of the great observational astronomers of the century, was not convinced. Christian Huygens was, and it was Huygens who took Romer's timings and turned them into an actual speed. The value they got was low by about a quarter, because the size of the Earth's orbit was not yet well known. But the important thing was not the number. The important thing was that light has a speed at all. Before Romer, the respectable position was that light propagates instantly. Descartes had argued for it strongly. If that had been true, the sky would be a live feed, and this entire video would have nothing to talk about. It took one man, one moon, and a set of eclipse timings nobody else wanted to sit through. So the sun is 8 minutes old. That's the headline. Now let's go one layer deeper, because the number is much worse than 8 minutes, and almost nobody hears this part. The light that leaves the sun's surface is new. The energy carried in it is not. Deep in the core, where hydrogen is being fused into helium under pressures and temperatures that have no useful comparison on Earth, a photon is produced. It sets off outward, and almost immediately it hits something, because the material there is dense enough that the photon travels a tiny distance, on the order of a fraction of an inch, before it is absorbed and re-emitted in a random direction. Then again, it is not traveling outward, it is staggering. Every step is in a random direction, and progress toward the surface happens only because there are so many steps that the wandering slowly adds up. This is the same statistical process that governs how a drop of ink spreads through still water, and it is agonizingly slow when the distance is 430,000 miles. Estimates for how long that journey takes vary a great deal, and I want to be honest about that rather than give you false precision. The figures you'll see published range from about 10,000 years to over 170,000 years, depending on how the interior is modeled. A commonly quoted middle figure is around 100,000 years. Take the middle figure and sit with it. The sunlight warming your face on a clear afternoon carries energy that was released in the core of the sun while our species was still confined to Africa. It began its journey before agriculture, before writing, before the last ice age. It spent that entire span bouncing around inside a star, and then crossed 93 million miles of empty space in 8 minutes and 20 seconds. The last leg was the quick part, which sets up the uncomfortable version of the question. If the sun stopped, right now, when would you find out? The honest answer is 8 minutes and 20 seconds, and it holds for everything, not just the light. This used to be an open question, because Newton's gravity worked as though it acted instantly across any distance. Einstein said it couldn't, and that gravitational influence must also propagate at the speed of light. We now have that measured. In August of 2017, the collision of two neutron stars was detected as a burst of gravitational waves, and about 1.7 seconds later, a burst of gamma rays arrived from the same event. So gravity and light run at the same speed, and there is no signal of any kind that could reach you sooner. Which means that in the scenario where the sun vanishes, the Earth continues along its curved orbit as though nothing has happened for 8 minutes and 20 seconds, because the gravitational news hasn't arrived either. The sky stays bright, your day continues, and then everything ends at once. I should say plainly that the sun is not going to vanish. Nothing in physics permits it, and this is a thought experiment rather than a forecast. But the structure of the thought experiment is the thing to keep, because we are going to meet real versions of it, and the structure is always the same. Something happens, the information about it travels at a fixed speed. Until it arrives, your world looks completely normal, and your fate is already fixed. That is stage 1. 8 minutes and 20 seconds. For the nearest star, the one we can see better than any object in the universe, that's the best case. That's the most warning anything in this video is going to give you. Now consider what happens when we stop looking at the star that's 8 light minutes away and start looking at one that's 640 light years away. Because if 8 minutes is enough to make the sun a historical record, then a star that far out isn't showing you the past. It's showing you a past so old that everything you know about it might have stopped being true while you were learning it. And there is one particular star, easily visible from your back garden, bright orange, sitting in the shoulder of the most recognizable constellation in the sky, where astronomers will tell you quite calmly that it may have already exploded. That's the second stage, and it's where this stops being a thought experiment. Go outside tonight, in winter, and find Orion. It is the easiest constellation in the sky to pick out, because of the 3 stars in a row that make the belt, and almost everyone can find it without help. Now look up, and to the left of the belt, at the shoulder, there's a star there that is noticeably orange, even to the naked eye, in a sky where almost everything else reads as white or faintly blue. That's Betelgeuse, and I want you to hold in your mind, while you're looking at it, that there is a genuine possibility you are looking at something that no longer exists. This is the second stage, and the warning time here is 640 years. Let me be precise about what that means, because it's easy to say and easy to hear wrong. Betelgeuse is roughly 640 light-years away. The light hitting your eye tonight left that star around the year 1386. Richard II was on the English throne. Chaucer was working on the Canterbury Tales. The Ming dynasty was 18 years old. Everything that has happened to Betelgeuse since then is still in transit. If that star exploded in the year 1400, the light announcing it is currently somewhere out in the dark, about 40 light-years short of us. And it will arrive in roughly 40 years, and there is no observation anybody can make tonight that would tell us. Not with a bigger telescope, not with a better detector. The information is not here yet, and no instrument can collect information that hasn't arrived. That is a strange kind of ignorance, and it is worth naming clearly. It isn't that we don't know enough, it's that the fact does not yet exist in our vicinity. Now let's talk about the star itself, because it is a genuinely extraordinary object, and the numbers are hard to hold on to. Betelgeuse is a red supergiant. Its mass is somewhere around 15 to 20 times the Sun's, and the uncertainty there is real. But mass is not what makes it remarkable. What makes it remarkable is its size. Estimates put its radius at something like 700 times the radius of the Sun. Try to make that concrete. If you remove the Sun and put Betelgeuse in its place, with the center in the same spot, the surface of that star would extend past the orbit of Mercury, past Venus, past Earth, and out roughly to the orbit of Jupiter. Everything we call the inner solar system would be inside the star. You would not be standing on a planet looking at it. You would be somewhere in its outer layers. And it is not a solid thing with a clean edge. A red supergiant has an atmosphere so tenuous and so extended that asking where it ends is not really a well-posed question. The surface boils in cells the size of the Earth's orbit. It sheds mass continuously. It is, in a real sense, coming apart slowly, and has been for some time. This is what a massive star looks like near the end. It has burned through the hydrogen in its core, swollen enormously, and begun working through heavier fuels, each stage faster than the last. Hydrogen burning lasts millions of years. Helium burning? Less. By the time a star of this mass is fusing silicon into iron, that stage lasts about a day, and then it stops, because iron does not release energy when it fuses, it absorbs it. The core, which had been holding the star up by the pressure of its own furnace, loses that support in under a second, and collapses at roughly a quarter of the speed of light. That collapse is the supernova. And here is the thing worth pausing on, because it is easy to treat all of this as theory. Human beings have watched it happen, several times, and every single time, they were watching something that had finished long before any of them were born. The best documented case is from the summer of 1054. Court astronomers in China, whose job was to monitor the sky and report anything unusual to the emperor, recorded the appearance of what they called a guest star, in the region we now call Taurus. Their records are unusually precise because this was administrative work rather than curiosity, and administrators write things down. The guest star was bright enough to be visible in broad daylight for 23 days. It remained visible at night for close to 2 years before fading away entirely. The same event appears in Japanese records and in Arabic ones. There are claims that it appears in rock art in the American Southwest, and I will flag honestly that those claims are debated and not settled. Point a telescope at that spot today and you find the Crab Nebula, a tangled shell of glowing gas with a rapidly spinning neutron star at its center. It is expanding, and you can measure the expansion rate, and you can run it backward. It arrives at the year 1054, and you can go and look at it. That is the part I would encourage you to actually do. The Crab Nebula sits in Taurus, not far from Betelgeuse in the winter sky, and a modest backyard telescope will show it to you as a faint grey smudge on a clear night. When you look at that smudge, you are looking at the debris of an explosion that a Chinese official wrote down on a specific date, in a specific reign, because it was his job to notice. You and he are looking at the same object. He saw it happening. You are seeing what is left, and both of you are about 6,000 years late, because that is roughly how long the light takes to get here. Then 5 centuries later, one appeared at exactly the right moment to break something. On the 11th of November, 1572, a young Danish nobleman named Tycho Brahe was walking back to dinner and looked up, and there was a star in Cassiopeia that had not been there. He did not trust his own eyes. He stopped servants on the road and asked them whether they could see it too. Now, to understand why this mattered so much, you have to know what educated Europeans believed about the sky at the time. The inherited Aristotelian view held that everything above the sphere of the moon was perfect, eternal and unchanging. Change happened down here. Up there, nothing was ever new. A new star was not surprising under that framework. It was impossible. Tycho was the finest naked-eye observer who has ever lived, and he did the correct thing. He tested whether the object was near or far by checking for parallax, whether it shifted position against the background stars as the Earth rotated and as the seasons progressed. Anything close, like a comet in the upper atmosphere, would shift. Anything far would not. Put yourself in his position for a second, because it is easy to underrate what he did. You have been taught your entire life that the heavens cannot change. You walk outside and the heavens have changed. Everyone around you can see it too, so you are not unwell. You have 2 options. You can decide the object must be close, some kind of atmospheric phenomenon, which would leave your entire worldview intact. Or you can go and measure, knowing that one of the possible answers destroys something you believe. He measured for months and found no shift at all, which meant the new object was out among the fixed stars, in the region that was supposed to be incapable of change. He published a small book about it, and the title gave us a word we still use. He called it De Nova Stella, the new star. 32 years later, in October of 1604, another one appeared, and Johannes Kepler observed it for a year and wrote it up in similar detail, and then it stopped. That was 422 years ago, and no supernova in our own galaxy has been seen with the naked eye since. This is genuinely odd, because the expected rate for a galaxy like ours is on the order of 1 to 3 per century. We should have had a dozen or more since Kepler. The likely explanation is dust. Our solar system sits inside the disk of the Milky Way, so we look at our own galaxy edge-on, through the thickest possible layer of obscuring material. Most of those explosions almost certainly happened on schedule, and their light was absorbed before it got here. We know of at least one for certain. There is a remnant in the direction of the galactic center, expanding fast enough that the explosion must have occurred around the 1870s. Nobody saw it. Nobody recorded anything. The light arrived at Earth during the lifetime of people whose photographs we have, and it was swallowed by dust on the way. So the record is this: 3 supernovae watched carefully by human beings in 2,000 years, each one an event that had concluded thousands of years before the observer was conceived, and an unknown number of others that happened and were simply never delivered. Now, here is the part of this story where the sky did something genuinely alarming, and where the human vignette comes in, because a handful of people noticed it before anyone else. In October of 2019, Betelgeuse started getting dimmer. At first, this was unremarkable. Betelgeuse is a variable star, and has been known to be one for a very long time. It brightens and fades on a rough cycle of around 400 days, and amateur astronomers have been logging those changes for over a century. A dip is normal. This dip did not stop. Edward Guinan and Richard Wassertonic at Villanova University had been monitoring Betelgeuse photometrically for decades, which is exactly the kind of unglamorous long-term work that nobody notices until it matters. By December of 2019, they had watched it fall to the faintest level in the whole history of their record, and they published a short astronomical telegram saying so. That notice went out to the community 2 days before Christmas, and it changed the winter for a lot of astronomers. By February of 2020, Betelgeuse had dropped to roughly 40% of its normal brightness. You could see the difference with your own eyes, standing in a car park, without any equipment at all. A star that is normally among the 10 brightest in the night sky had visibly faded out of the top 20. People who had known that constellation their whole lives noticed that Orion looked wrong. And the obvious question, the one that got asked in every newsroom on Earth, was whether this was the collapse beginning. It wasn't. But working out that it wasn't took real effort, and the answer turned out to be more interesting than the scare. Andrea Dupree at the Harvard and Smithsonian Center for Astrophysics had been observing Betelgeuse in ultraviolet light with the Hubble Space Telescope, and she had something almost nobody had: coverage of the star from before the dimming, through it, and out the other side. What that record showed was material moving. In the months before the star faded, dense hot gas was traveling outward through the atmosphere on the side of the star facing us. The picture that emerged, published across 2020 and 2021, was that Betelgeuse had ejected a large piece of its own surface. That material moved out, cooled as it expanded, and condensed into dust, and the dust sat between us and the star, and blocked the light. So the star did not dim. We were looking at it through a cloud of its own debris, which it had thrown at us. I find that more unsettling than the supernova story, and I want to be clear about why. A supernova would have been the star doing the thing we already expected. This was the star doing something nobody had watched happen before, at close range, on a timescale of months, visible to the naked eye. The scale of the ejection was estimated at several times the amount of material the Sun loses in an entire year, gone in one event. By spring of 2020, the brightness recovered, the dust dispersed. Orion looked normal again. So, is it going to explode? Here is where I want to be honest rather than dramatic, because this is the point in a video like this where the temptation is to overclaim, and the overclaim is what makes people stop trusting the channel. Yes, Betelgeuse will explode. That is not in question. A star of that mass has exactly one ending available to it. When is the question? And the honest answer is that the error bars are enormous. Published estimates for the remaining lifetime typically run from a few thousand years up to 100,000 years or more. On a human timescale, that is indistinguishable from never. On an astronomical timescale, it is imminent. Both statements are true, and they are describing the same number. There is also an ongoing argument about the distance itself, which matters because almost every other property is derived from it. 640 light-years is a common figure, but you will see values ranging from about 500 to about 700, depending on the method, and the uncertainty is stubborn. Parallax works badly here, because the star is so large and its surface so blotchy that its apparent center wobbles for reasons that have nothing to do with its actual position. We are trying to measure the distance to a thing that will not hold still. And now the question you're waiting for. If it goes, are we in danger? No. And I want to say that plainly rather than leave it hanging, because the honest answer is genuinely reassuring and there's no reason to withhold it. The rough threshold at which a supernova starts to matter for a planet is somewhere around 50 light-years, and even that figure is debated. The radiation reaching us would be trivial. What you would get instead is a show. For several weeks it would be the brightest object in the night sky by a wide margin, comparable to the full moon but concentrated into a single point, which is a thing no living human has seen. It would be visible in broad daylight. It would cast shadows at night. Then over months it would fade, and after a year or two, it would be gone from the naked eye, and the winter constellation that every culture on Earth has a name for would be permanently missing a shoulder. Every human being alive would watch it happen, and the event itself would have finished 640 years earlier. So that's stage 2, and notice what it actually did. It didn't threaten you. It demonstrated something, using an object you can walk outside and look at tonight, that a thing can be over, completely and irreversibly, while it still appears in your sky, unchanged, every single night, for centuries. Betelgeuse is the safe version of that lesson. Now let's take the same structure and point it at something that is not safe, that is not 640 light years away, and that has already hit us twice in recorded history. Because our own star does something on a regular schedule that would do far more damage to your actual life than a supernova ever could. And with that one, the warning time is not centuries, it's about 15 hours. Except, as we'll see, that number is a lie too. On the morning of September 1st, 1859, a wealthy amateur astronomer named Richard Carrington was in his private observatory at Redhill, just south of London, doing what he did most clear mornings. He had a telescope projecting an image of the sun onto a screen, and he was tracing the outlines of sunspots by hand onto paper. It was routine work. He had been doing it for years, and the whole point of it was consistency, the same measurement, made the same way, day after day, until a pattern emerges. At around 11:18 in the morning, 2 points of intensely bright white light appeared inside the sunspot group he was drawing. Carrington's first thought was that something had gone wrong with his equipment. He assumed a gap had opened in the cloud cover and was letting unfiltered sunlight through onto his screen. He went to check. Nothing had changed. The light was on the sun. He ran to fetch someone else to look, and by the time he got back, roughly a minute later, the 2 points had already faded substantially. The whole event lasted about 5 minutes from start to finish. 17 years of watching the sun, and he happened to be looking directly at the one spot on its surface where this was happening, during the 5 minutes it lasted. A few miles away, another English astronomer named Richard Hodgson saw the same thing independently, which is the only reason anybody believed either of them. What Carrington had just witnessed was the first solar flare ever observed by a human being, and attached to it was something he could not see and had no way to know about, which was already on its way to Earth. This is the third stage. Call it the storm already launched. Let me set up the physics simply, because the mechanism here is the whole point of the stage, and it's not complicated once you see it. The sun regularly throws material off itself, not light, not radiation, but actual matter, a cloud of charged particles, billions of tons of it, launched outward at enormous speed. This is a coronal mass ejection, and it happens on the order of a few times a week during the active part of the sun's cycle. Most of them go in directions that miss us entirely, which is what you would expect, since the Earth is a very small target and space is mostly empty. Now here is the part that matters for tonight. The flare, the flash of light Carrington saw, travels to Earth at the speed of light, 8 minutes and 20 seconds. The cloud of matter travels much slower. A typical coronal mass ejection crosses the distance in 1 to 3 days. So for once, the universe gives you something it almost never gives you. The light arrives first and it tells you the event happened. That gap between the flash and the arrival is your warning window, and it is the only real warning window anything in this entire video provides. Everything else tonight gets progressively worse. The Carrington Event's cloud made the crossing in about 17.5 hours, which is extraordinarily fast. The reason it was that fast appears to be that another ejection had gone off shortly before it and effectively cleared a path through the solar wind, so the second one had an easier run. Then it hit. What happened next is the reason this event still gets talked about in engineering meetings 167 years later. Aurora, which you normally have to travel toward the poles to see, appeared over Cuba, over Hawaii, over Colombia and Queensland. In the northeastern United States, people reported being able to read a newspaper outdoors at 1 in the morning by the light of the sky. Gold miners in the Rocky Mountains got up and started cooking breakfast because they assumed it was dawn. And the telegraph network, which in 1859 was the only piece of electrical infrastructure that existed anywhere in the world, stopped behaving. Operators received electric shocks from their equipment. Paper caught fire in some offices from sparking. And then something genuinely strange happened, which is the detail I find hardest to shake. Some operators discovered they could disconnect their batteries entirely and keep transmitting, because the current induced in the wires by the storm was enough to carry the signal on its own. 2 operators, one in Boston and one in Portland, ran their line on nothing but the aurora for around 2 hours. Now understand what that means, because this is where the stage turns from a historical anecdote into something about you. A geomagnetic storm induces currents in long conductors. In 1859, humanity had a few thousand miles of telegraph wire. Today we have millions of miles of high-voltage transmission line. And the thing at the end of those lines is a transformer. And a large grid transformer is a piece of equipment that weighs hundreds of tons, is often custom-built, and can take a year or more to replace. They are not sitting in a warehouse waiting. We have seen a small preview of this. On March 13, 1989, a geomagnetic storm considerably weaker than the Carrington Event induced currents in the Hydro-Quebec power grid. The system went from normal operation to total collapse in 92 seconds. 6 million people lost power in Canada in March, and it took about 9 hours to restore. 92 seconds is not enough time for a human being to make a decision. It is barely enough time to notice. It is worth understanding exactly what breaks, because the failure mode is specific and slightly counterintuitive, and once you see it, the concern stops being vague. A power grid runs on alternating current. Everything in it, and particularly the transformers, is designed around current that reverses direction many times a second. The current a geomagnetic storm induces in a long transmission line does not do that. It drifts slowly in one direction, which from the transformer's point of view is essentially direct current, and a transformer has no idea what to do with that. What happens is that the steady component pushes the transformer's iron core into saturation for half of each cycle. A saturated core stops behaving like a transformer core. It draws enormous reactive current. It generates stray magnetic fields that were never supposed to exist inside the housing. And those fields dump heat into the windings and the structural steel. And that heat appears in the wrong places. A transformer is engineered to move heat out of the regions that normally get hot. These are not those regions. The insulation cooks. Some units fail during the storm. Others survive it, and then fail quietly weeks or months later, because the insulation was degraded and nobody could see it. Now add the logistics. The large transformers at the top of a transmission network are not off-the-shelf equipment. They are frequently built to order for a specific installation. They weigh in the range of 200 to 400 tons, and lead times from order to delivery are typically measured in many months and sometimes years. There is no warehouse of spares, because storing them would cost more than the risk appeared to justify. And then the dependency chain closes on itself, which is the part that makes engineers uncomfortable. Without power, you cannot pump water. You cannot pump fuel because the pumps are electric. You cannot run refrigeration for food or for medicine. And you cannot run the industrial plants that would build the replacement transformers. Take a moment and actually apply that to your own house, because it is more instructive than any figure I can give you. Your lights go out, and you are annoyed rather than worried, because this has happened before and it always comes back. That is the correct reaction for the first day. On the second day, you notice that the water pressure has dropped, because the pumps that push water up into your building or your street are electric, and the reservoirs that feed them run on gravity for a while and then stop. You go to fill your car, and the pump does not work, because it is also electric, and the fuel underneath it is fine and completely inaccessible. Your phone works until the battery goes, and the tower it was talking to works until its backup generator runs out of the fuel you cannot pump. And every one of those problems is trivially solvable if you have electricity, which is the entire point. It is not that a solar storm destroys anything you would notice. It removes one input, and almost everything else you depend on turns out to have been quietly built on top of it. None of this requires the worst case. Quebec was 9 hours, and 9 hours is an inconvenience. What changes the character of it is duration, and duration is set by how many transformers have to be replaced rather than repaired. Take a moment and walk through your own week without it, because the exercise is more instructive than any number I can give you. Your lights are the least of it, and you would sort that out in a day. Your water arrives at your home because something is pushing it, and that something is electric. Your food is where it is because a chain of refrigerated buildings and trucks kept it cold, and that chain is electric from end to end. If you drive, the fuel in the ground under the filling station stays in the ground because the pump is electric. If you take medication that needs to be kept cool, you have a few days. And you would not be able to find out what was happening because the phone in your pocket depends on towers that hold up for a matter of hours on their batteries. None of that requires the dramatic version of this scenario. A regional outage of a week does all of it, and you can find people who have lived through exactly that after a hurricane and will tell you what the second week is like. We got a smaller demonstration in late October and early November of 2003. In a run of storms that got called the Halloween events. Aurora were visible from Texas and Florida. A transformer in South Africa was damaged badly enough to be taken out of service. Part of the city of Malmö in Sweden lost power for about an hour. Satellite operators put spacecraft into protective modes. Some instruments were damaged permanently, and the crew aboard the space station were told to move into the most shielded part of the structure. That was a serious storm. It was not a Carrington event. Now, I want to give the other side properly, because this is a subject where the alarming version circulates much more freely than the measured one. There are engineers who argue that the worst-case scenarios are overstated. Their case is that modern grids have protective relays that disconnect equipment automatically when conditions go out of range, that the resulting blackout is itself protective, and that a system which trips offline early loses power but keeps its hardware. On that view, the outcome of a Carrington-class event is a large, expensive, and genuinely disruptive blackout of days to weeks, rather than a multi-year continental failure. I do not think that argument has been settled, and I am not going to pretend it has. What I will say is that both sides agree on the direction. The event is possible, the exposure is real, and preparation is cheap relative to the range of outcomes, and there are people whose entire job is the 15 minutes. There is an operations floor, staffed continuously, where forecasters watch the sun the way meteorologists watch a coastline. They track active regions as they rotate into view. They model whether an ejection is aimed at us, and when the spacecraft at L1 reports the magnetic field orientation, they are the ones who decide, in that quarter of an hour, whether to tell the grid operators and the airlines and the satellite fleets that it is time. It is one of the stranger jobs on the planet. Most days nothing happens. That is the whole point of it. And then there is the one that missed. On July 23, 2012, the Sun launched a coronal mass ejection that current analysis puts in the same class as the Carrington event, possibly stronger. It crossed the Earth's orbit at high speed. The Earth was not there. We had been at that point in our orbit about 9 days earlier. The only reason we know the details is that one of the stereo spacecraft which was in a position to watch flew through it and measured it directly. Daniel Baker at the University of Colorado, who led the analysis, summarized the situation in a way that has been quoted ever since. If it had hit, we would still be picking up the pieces. The estimates for what a direct Carrington-class hit would cost a modern grid vary enormously, and I would rather give you the range than a single confident figure. Studies from Lloyd's of London and from the National Academy of Sciences have produced numbers from several $100 billion up to a few trillion, with recovery times from months to years in the worst regional scenarios. Those are estimates built on models of a thing that has never happened to an electrified civilization. Treat them as order of magnitude, not as forecasts. But now let's get to the part I promised, which is that the warning time is not really 15 hours, because here is the problem, and it is a genuinely elegant piece of bad news. When you see the flare, you know something was launched. You do not know whether it's coming at you, and more importantly, you do not know the one thing that determines whether it does damage. A coronal mass ejection carries a magnetic field with it. Whether that field does serious harm to the Earth depends almost entirely on which way it's pointing. If the field is oriented northward, it largely bounces off our own magnetic field and the effects are mild. If it is oriented southward, it links up with ours and the energy pours in. Same cloud, same speed, same mass, opposite outcomes, depending on an orientation you cannot measure from here. So how do you find out? You wait for it to arrive at a spacecraft. There is one sitting about 1 million miles upstream of us, at a gravitational balance point called L1, and its job is to be hit first. It measures the field orientation and radios the result home at the speed of light. 1 million miles sounds like a comfortable distance. It isn't. The cloud is moving at somewhere between 700,000 and several million miles an hour, and it covers that last million miles in something like 15 to 60 minutes. That is your actual warning. Not a day, not 15 hours, between a quarter of an hour and an hour, arriving after 30 hours in which you knew something was coming but not whether it mattered. It is enough time to do a few specific things. Grid operators can reduce load, bring transformers offline, and reconfigure the network to limit the induced current. Satellite operators can put spacecraft into safe modes. Airlines can reroute polar flights. Those actions are real, and they meaningfully reduce the damage, and the people who do them are quietly one of the more useful groups of professionals on the planet. It is not enough time to prepare a society. It is enough time to brace. So that is stage 3, and here is what it added to the argument. Stage 1 told you the sky is old. Stage 2 told you something can be over while it still looks fine. Stage 3 is the first one where the delay is actually working in your favor, because the danger travels slower than the news about it, and that gap is the only reason we can do anything at all. Hold on to that, because it is the last time tonight it will be true. From here the gap closes. In the next stage the news and the object arrive together, and after that the object arrives first, and the news comes afterward, months later, from an astronomer looking at old data and realizing what went past. On February 15th, 2013, the world's astronomers were watching an asteroid. They had known about it for a year. It was called 2012 DA14. It was about 100 feet across, and it was going to pass closer to the Earth than our own communications satellites. The pass was predicted. The timing was known to the second. Telescopes were booked, and news organizations had scheduled coverage. That afternoon, it passed exactly where the calculations said it would, and nothing happened, which is what a successful prediction looks like. 16 hours earlier, on the other side of the planet, a completely different rock that nobody had ever seen entered the atmosphere over the Russian city of Chelyabinsk at 9:20 in the morning, local time. It arrived from the direction of the sun. This is the 4th stage, and the warning time is somewhere between a few hours and nothing at all. Let me tell you what that morning was actually like, because Chelyabinsk is the best documented impact event in human history, and the reason is almost funny. Russian drivers fit dashboard cameras in large numbers, mostly because of problems with insurance fraud and disputed liability. So when a rock the size of a house came in over a city of over 1 million people on a workday morning, several hundred cameras were already recording, pointed in every direction, with timestamps. We have this event from more angles than we have most things that happen on purpose. The object was roughly 62 feet across and weighed something like 12,000 tons. It entered the atmosphere at about 41,000 miles an hour, at a shallow angle, which meant it had a long way to travel through thickening air. At that speed, air does not move out of the way. It compresses in front of the object faster than it can flow around it, and compressed air gets extremely hot. The rock began to glow, then to shed material, then to come apart under the stress. About 18 miles up, it broke apart entirely, and the energy released in that airburst was somewhere around 500 kilotons. For comparison, the weapon used at Hiroshima was around 15. So roughly 30 times that, released in the sky over a city. For about 5 seconds, it was brighter than the sun. People stopped their cars, they got out, they stood in the street and looked up, and then, because it was 5 degrees below freezing and this was a normal Friday, they went inside and walked to their windows to keep watching the smoke trail hanging in the sky. And this is the part that belongs in tonight's video specifically, because it is the same physics as everything else we have talked about, operating on a scale you can feel. The light arrived instantly, the shockwave did not. Sound travels through air at roughly 760 miles an hour. The airburst happened 18 miles up and some distance away. So there was a gap in most of the city of between 1 and 3 minutes between seeing the flash and the arrival of the pressure wave. Everybody spent that gap walking toward glass. When the shockwave hit, it blew in windows across roughly 7,200 buildings. Around 1,500 people were injured badly enough to seek medical treatment, and the overwhelming majority of those injuries were lacerations from flying glass, sustained by people standing at windows, watching the sky, because the thing that hurt them was still on its way, and there was nothing to hear yet. Nobody died. That is genuinely remarkable, and it comes down to the angle of entry and the altitude of the burst. But hold on to the shape of it. A signal arrived at the speed of light. It told everyone that something had happened. And the thing itself was still 3 minutes out, and everyone used those 3 minutes to put themselves in the worst possible position because the warning did not come with instructions. Now, why did nobody see it coming? Not because we weren't looking. In 2013, there were multiple survey telescopes systematically scanning the sky for exactly this. The Chelyabinsk object was not missed through carelessness. It was undetectable, and the reason is pure geometry. Optical telescopes on the ground find asteroids by seeing sunlight reflected off them. To do that, you need a dark sky, which means you need to be pointed away from the sun. So every night, all over the world, we search the anti-solar direction, and we do it well. An object approaching from the direction of the sun is in the daytime sky. It is drowned in scattered sunlight from the atmosphere, and even if you could somehow see through that, the geometry means you are looking at its unlit side. It is a dark object against a bright background in the one direction your instruments cannot point. There is a whole population of asteroids on orbits that keep them mostly interior to ours. They spend the large majority of their time in exactly that blind spot. We are not scanning it because we cannot. And this is not a rare edge case. It is a permanent structural hole in our coverage, and it has been there since we started looking. If you want the version of this that gets closest to being a problem, it happened on July 25, 2019. An asteroid designated 2019 OK passed the Earth at a distance of about 45,000 miles. That is roughly a fifth of the way to the Moon, which in the context of the solar system is not a near miss. It is effectively a graze. It was around 330 feet across. Run the comparison. Chelyabinsk was 62 feet and took out the windows of a city. This object was more than 5 times that in each dimension, which puts its mass over 100 times higher. It was not a window breaker. Michael Brown, an astronomer at Monash University in Australia, described it in the press at the time as a city killer, and he was not being theatrical. It was detected the same day it passed. Astronomers at the SONEAR Observatory in Brazil and at the ASASSN survey picked it up within about 24 hours of closest approach, and the analysis confirming what had just happened was finished after it had already gone by. A rock large enough to destroy a metropolitan area passed inside the orbit of the Moon, and the human species learnt about it as it was leaving. And if you want to know what the next size up actually does, we have a case, and it happened within living memory of people whose voices were recorded. On the morning of the 30th of June, 1908, something entered the atmosphere over a remote stretch of Siberia, near the Podkamennaya Tunguska River. It was probably somewhere between 150 and 200 feet across, and like Chelyabinsk, it never reached the ground. It broke apart in the air, around 5 miles up. The blast flattened roughly 830 square miles of forest. To make that land on you rather than sit there as a number, It is an area larger than the metropolitan region you probably live in, and if you were standing at the edge of it, you would not be able to see across it. Estimates put the number of trees knocked down at around 80 million. Seismic stations across Europe and Asia registered it. Barometers recorded a pressure wave that traveled around the entire planet twice. And for several nights afterward, the skies over Europe were bright enough at midnight that people reported being able to read outdoors, which is the second time tonight that particular detail has come up, from a completely different cause. There were very few people underneath it, and that is the only reason this is a curiosity rather than the defining catastrophe of the 20th century. Because here is the arithmetic that gets quoted, and it holds up. The Earth turns once every 24 hours. If that object had arrived about 4 3/4 hours later, the rotation of the planet would have placed St. Petersburg, a city of 1.5 million people, under the point of the airburst. Not near it, under it. And I want you to notice how thin that is, because it is not a comforting kind of luck. Nothing steered it. Nothing chose. The object was on its trajectory for millions of years, and the Earth was turning at the rate it has always turned, and the two of them intersected over swamp and pine forest rather than over a capital city for no reason at all. Roll the same event 4 3/4 hours in either direction and it lands somewhere else. You can do that arithmetic for any impact, anywhere, and the answer is always the same. Whether an object hits a city or an ocean is set by what time of day it arrives, and nothing in the universe is arranging for it to be a convenient hour. Nobody went to look for 19 years. The region was almost inaccessible. The country went through a revolution and a civil war, and the reports from the few local witnesses did not reach anybody with the means to investigate. The man who finally went was a Russian mineralogist named Leonid Kulik, who mounted an expedition in 1927. Travelling by river and on foot into an area with no roads. He was looking for a crater, and there wasn't one, and for a while he assumed he was in the wrong place. Then he understood what he was looking at. The fallen trees were lying in a radial pattern, all pointing outward from a single centre, across an enormous area, like grass flattened by something set down on top of it. And at the exact centre, the trees were still standing. Upright, stripped completely bare of branches and bark, but standing. That detail is what told him the blast had come from directly overhead. A shock wave arriving straight down pushes a tree straight down, and a bare vertical trunk survives it. Everywhere else, the wave arrived at an angle and pushed the trees over. A forest of stripped vertical poles, surrounded by 830 square miles of trees lying flat in a circle, 19 years after the fact, with the man who came to look for the crater standing in the middle of it. Which brings me to the person who turned all of this from anecdote into a science, because for most of the 20th century, impacts were not taken seriously by geologists at all. Eugene Shoemaker was a young geologist working in Arizona in the 1950s, and he became convinced that the large hole in the desert near Winslow, then generally attributed to a volcanic steam explosion, was in fact an impact crater. He could not prove it by looking at the shape, because shape is arguable. So he went after the rock chemistry, and he and a colleague found a mineral called coesite in the crater walls. Coesite is a form of silica that only forms under the kind of pressures you get from a hypervelocity impact. Volcanoes do not make it. That was the proof, and it opened the door to a realization that changed planetary science. The craters covering the moon, which had also been widely attributed to volcanism, were impacts too, and the same process had happened here and been erased by weather and plate tectonics. Shoemaker went on to train the Apollo astronauts in field geology, so that when they got to the moon, they would know what they were looking at. He had wanted to go himself, and was medically disqualified, and by his own account, it was the great disappointment of his life. He spent the rest of it hunting craters, and in 1997 he was killed in a car accident in the Australian outback, on a field trip looking for exactly that. The following year, a small capsule containing some of his ashes was carried to the moon aboard a spacecraft and deliberately crashed into a crater near the South Pole. He is the only human being buried on another world. So what is actually being done? Because I do not want to leave you with the impression that nobody is working on this, and the honest picture includes some real progress. In 2005, the United States Congress set a target: find 90% of near-Earth objects 460 feet across and larger. To make 460 feet concrete, that is a little taller than the Great Pyramid at Giza, and an object that size striking land would destroy an area the size of a large city and its surroundings. The deadline was 2020. We did not make it. Current estimates put the fraction found at somewhere around 40%, and that number should be treated as approximate because it is an estimate of a fraction of a population whose size we are also estimating. For the genuinely civilization-ending sizes, above about half a mile, the picture is much better. We believe we have found well over 90% of those, and none of the ones we have found are on a collision course. That is real, and it is worth saying. The dangerous gap is in the middle, big enough to level a city, small enough to hide. The main answer to that is an instrument called NEO Surveyor, an infrared space telescope designed specifically to solve the geometry problem. The trick is that it does not look for reflected sunlight, it looks for heat. An asteroid sitting in sunlight is warm, and it glows in the infrared regardless of which side is lit, and from a position out in space you can look much closer to the sun than you ever could from the ground. It is planned for launch toward the end of this decade. It will substantially close the gap. I want to be careful here rather than oversell it. It will not eliminate the blind spot because some geometries remain genuinely hard, and finding an object is not the same as finding it in time. Because finding it in time is the entire game, and we now know that for certain because we tested it. On September 26, 2022, a spacecraft roughly the size of a vending machine flew into an asteroid called Dimorphos at about 14,000 miles an hour. It was called DART, and the entire mission existed to answer one question. If you hit a rock, does the orbit change by a useful amount? The last images came back from a camera on the spacecraft, and they are worth describing, because they are among the strangest photographs anybody has ever taken. The asteroid starts as a dot, then a shape, then a surface, then individual boulders, resolved, filling the frame. Then the final image is incomplete, a partial transmission, cut off mid-frame at the moment the camera stopped existing. The impact shortened the object's orbital period around its companion by about 32 minutes. The mission's own success criterion had been 73 seconds, so deflection works. That is one of the genuinely good pieces of news in this entire subject, and it was earned by a specific team of people who spent years on it. But look at what it requires. To move an object usefully, you need to change its speed by a tiny amount, a long time in advance, so that the tiny change has years to grow into a miss. Deflection is not a thing you do to an incoming rock. It is a thing you do to a rock that arrives in 15 years. Which means the capability is real and completely useless without warning, and warning is exactly the thing the geometry takes away. That is stage 4. The news and the object arrive together, and by the time you know, the only remaining decision is where to stand. Now let's go to the stage where they arrive in the wrong order. On the 19th of October 2017, a postdoctoral researcher named Robert Werrick was doing the least glamorous job in astronomy. He was going through the previous night's images from the Pan-STARRS-1 telescope on the summit of Haleakala on Maui, checking objects the software had flagged as moving. Most of them are nothing. Known asteroids, satellites, artifacts. One of them was moving wrong. Not fast in a way that was unusual, exactly. Wrong in its trajectory. When he and his colleagues fitted an orbit to it, the fit came back with a shape that does not happen. Every object that belongs to the Sun travels on a closed path, an ellipse. It goes out, it comes back, and however long that takes, it is bound. Comets on 100,000-year orbits are still bound. The mathematical measure of that is called eccentricity, and for anything that belongs here, it is less than 1. This object came back with an eccentricity of about 1.2. That is not a slightly unusual orbit. It is a different category of thing. It means the object is not on a closed path at all. It came in from outside the solar system, swung around the Sun, and is leaving, and it will never return, and it was never ours. The first confirmed visitor from another star, and we found it on the 19th of October. Now look at the calendar, because this is the whole reason it belongs in tonight's video. It had made its closest approach to the Sun on the 9th of September, 40 days earlier. It had made its closest approach to the Earth on the 14th of October, 5 days earlier. This is the 5th stage, and the warning time is negative. Let me put that as plainly as I can. An object from another star system entered our solar system, passed the Sun, passed the Earth, and started on its way out, and the entire astronomical profession of a technological civilization found out afterward. Not late. After. The closest it would ever come to us was already in the past on the day we learned it existed. The team named it Oumuamua, working with Hawaiian language experts, and the name is better than most names in astronomy. It translates roughly as a scout or messenger from the distant past reaching out to us, a first arrival, and it left in a hurry. At its closest to the Sun, it was moving at something like 196,000 miles an hour. As it recedes, it settles toward around 58,000 miles an hour relative to the Sun, and it will carry that speed out into interstellar space for as long as there is a universe to carry it through. Think about where you were in the autumn of 2017. Whatever you were doing that October, you were doing it while the first confirmed object from another star system was making its closest pass and starting to leave, and nobody on the planet knew, including every astronomer alive. You did not miss it through inattention. There was nothing to attend to. The information had not been processed yet, by anyone. It is out past Neptune now. It is not coming back. And nobody will ever get a better look at it than the few weeks of observations we scrambled together after realizing what it was. That scramble produced 2 genuine puzzles, and I want to walk through them carefully, because this is a topic where a lot of nonsense gets said confidently, and I would rather give you the actual state of the argument. The first puzzle was the shape. Nobody ever resolved Oumuamua as anything but a point of light. It was far too small and too far away. But you can learn about shape from brightness, because as an irregular object tumbles, it presents different cross-sections to you, and the amount of sunlight it reflects rises and falls. Oumuamua's brightness varied by roughly a factor of 10 over a period of about 7 1/3 hours. That is an enormous swing, and the straightforward reading is that the object is extremely elongated. Estimates put the ratio of its long axis to its short axis at somewhere around 6:1, possibly more, something like a cigar, or, on other analyses that fit the data at least as well, something like a flattened disk. Either way, there is nothing in our solar system shaped like that. Asteroids are lumpy potatoes. This was a splinter. The second puzzle was the acceleration. As Oumuamua moved away from the Sun, it was not slowing down as fast as gravity said it should. There was a small extra push, directed away from the Sun, and it was measured well enough that it was not in doubt. Now, for a comet, this is completely ordinary. Comets warm up, ice turns to gas, the gas jets off, and the object gets a gentle push. We see this constantly. But a comet doing that is visible. The escaping gas carries dust with it, and you get a coma and a tail, and that is the most recognizable thing in the sky. Oumuamua had none. Deep imaging found no dust, no coma, no tail, nothing. So it was behaving like a comet and looking like a rock. The proposed explanations are numerous, and I will give you the honest spread. One line of argument is that it was outgassing something that does not produce a visible dust tail. Hydrogen ice has been proposed. Alan Jackson and Stephen Desch argued for a fragment of nitrogen ice chipped off a body like Pluto in another star system, which would sublimate and push without ever showing dust. Another line is that it was extraordinarily low in density, essentially a fluffy fractal aggregate, light enough for sunlight itself to push it measurably. And there is the proposal you've probably heard of, from Avi Loeb at Harvard, that its properties are best explained by an artificial object, a light sail. I want to represent that fairly and also accurately. It is a real proposal from a serious astronomer, published and argued in the literature. It is also a distinctly minority view. The large majority of the field regards the natural explanations as sufficient and considers the artificial hypothesis to be reaching well beyond what thin data can support. You should know the argument exists. You should also know where it sits. My own honest position is the boring one. We got a few weeks of poor data on an object we will never see again, and there is not enough there to settle it, and there probably never will be. That is unsatisfying, and it is where the evidence leaves us. Then, less than 2 years later, an amateur found the second one. Gennady Borisov is an astronomer at a Crimean observatory, but the telescope that made this discovery was not the observatory's. It was a 26-inch instrument that he had designed and built himself at home for his own use. On the 30th of August 2019, he was observing in the pre-dawn hours in the direction of the sun, which is the awkward part of the sky most surveys skip, and he found a moving object with a fuzzy edge. The orbit came back hyperbolic, eccentricity around 3.4, which is dramatically more unbound than Oumuamua. And this one was an ordinary comet. It had a coma. It had a tail. Spectroscopy found the molecules you would expect. Something formed around another star, by processes we would recognize, out of material we would recognize. That result is easy to skip past, and it is one of the more quietly profound things anybody has learned this century. Comets around other stars are made of roughly the same stuff as comets around ours. And here is the detail from that story that I keep coming back to. The second confirmed object from another star system was found by one man, before dawn, using a telescope he built with his own hands. A third interstellar object was found in 2025, picked up by the ATLAS survey. The important thing about that is not the object, it is the interval. It took us until 2017 to find the first, then 2 years for the second, and a few more for the third. The rate is climbing, and the reason has nothing to do with the objects. They were always coming through. The estimates suggest that at any given moment there is a meaningful population of interstellar objects inside the orbit of Neptune, and that we have simply never been able to see them. What has changed is us. The Vera Rubin Observatory in Chile is the instrument that turns this from luck into a census. It has a mirror 27 feet across, a camera of 3,200 megapixels, and an operating strategy unlike anything before it. Rather than pointing at targets, it photographs the entire available sky, over and over, every few nights, for years, and compares each image to the last. It is not a telescope for looking at things, it is a telescope for noticing that something changed, which is exactly the faculty we were missing. Think about how you spot something new in a room you know well. You do not examine every object. You notice that the picture is crooked because you have the previous version in your head to compare against. Until now, astronomy has mostly lacked that previous version. We have been walking into the room for the first time, every night. There is a useful way to think about what that changes. Right now, our knowledge of interstellar objects rests on a sample of 3. 3 is not a population. You cannot say anything statistical about a class of objects from 3 examples, and much of the argument about Oumuamua comes down to that. We have no idea whether it was typical or bizarre, because we have nothing to compare it to. The estimates for how many are actually out there are startling once you work backward from the detections. If we found one with a telescope that surveys a fraction of the sky, at a moment when it happened to be close and bright, then the underlying population has to be large. The figures people quote for how many interstellar objects are inside the orbit of Neptune at any given time run into the thousands, and some estimates go considerably higher. They are just small, dark, fast and unlit, which is the worst combination of properties an object can have if you would like to be seen. When that dataset matures, the expectation is that interstellar visitors go from a once-in-a-decade event to something found on a regular basis. And that matters for a reason beyond counting. Every one of these objects is a physical sample of another solar system, delivered here for free. We cannot go to other stars. We have no realistic prospect of going to other stars. But the material comes to us, continuously, and it always has, and until 2017 we simply never caught any of it. If we can find them early enough, rather than 5 days after closest approach, then some of them are reachable. A spacecraft launched at the right moment could fly past one. There is a mission being prepared for exactly this, parked in space, fueled, waiting, with no target, designed to launch at whatever turns up. That is a genuinely new kind of mission. Every previous probe was sent to something we already knew about. This one waits for something that does not exist yet. And that is genuinely the correct response to this stage, because the problem was never the objects. It was the latency between an event happening and a human being noticing, which is the point of stage 5, and it is a different point from the 4 before it. Stages 1 through 4 were about physics. The speed of light is fixed, and it sets a floor on how fast news can travel, and there is nothing to be done about it. Stage 5 is about us. Oumuamua's light was arriving at Earth for weeks before anybody read it. The photons were here. They were falling on the ground, on the ocean, on the roofs of observatories. The information had already made the journey and was sitting in our sky, unexamined, because nobody had pointed the right instrument at the right patch and run the comparison. That is a fixable problem, and we are fixing it. The next stage is not fixable, not with a better telescope, not with more survey time, not with any conceivable technology, because the limit is not our attention. In the next stage, the thing that kills you and the news that it is coming are the same photons, traveling together, arriving in the same instant. In 1963, the United States, the United Kingdom, and the Soviet Union signed a treaty banning nuclear weapons tests in the atmosphere, underwater, and in space. A treaty is only as good as your ability to check it, and checking the space clause was hard. So the United States built a series of satellites whose entire purpose was to sit in high orbit and watch for the gamma-ray flash of a nuclear detonation, including one hidden behind the moon. They were called the Vela satellites, from the Spanish verb meaning to keep watch. On the 2nd of July, 1967, one of them recorded a flash of gamma rays. The team at Los Alamos who received the data, including Ray Klebestadel, Ian Strong and Roy Olson, looked at the profile and could see immediately that it was not a bomb. A nuclear detonation has a characteristic signature, an intense initial spike, then a fast decay, and it is very recognizable once you know it. This was something else. 2 peaks, a different shape, a different duration. And here is what they did, which I think is the correct behavior, and also very hard. Nothing. They filed it and kept collecting. Over the next few years, more of these turned up. And because there were multiple satellites in different places, and gamma rays travel at a known speed, the arrival times differed slightly from one spacecraft to another, and that difference let them triangulate a direction. The directions did not point at the Earth. They did not point at the Sun. They pointed outward, at nothing in particular, all over the sky. Sit with what that must have been like for a moment, because you have almost certainly had a smaller version of it. You are employed to watch for one specific thing. You find something that is definitely not that thing, and definitely not nothing. You cannot explain it. You cannot publish it, partly because the program is classified, and partly because you have one event, and one event is not evidence. So you wait. For 6 years, collecting more, checking, and telling almost nobody, while the most energetic explosions in the universe arrive at your instrument every few weeks, and you have no idea that is what they are. In 1973, the team published 16 events in a short paper with a deliberately flat title about cosmic gamma-ray bursts. A weapons monitoring program, looking for one thing, had found a completely different one, and sat on it for 6 years until they were sure. This is the 6th stage, and the warning time is 0. Not 0 because we are not trying. 0 as a consequence of physics, permanently, with no possible remedy. Let me explain why. Because the reason is simple, and it is the cleanest illustration of this entire video. A gamma-ray burst announces itself with gamma rays. The gamma rays are the event. They travel at the speed of light, because light is what they are. Every previous stage tonight had a gap. The flare arrives before the plasma. The rock's flash arrives before its shockwave. Betelgeuse's light will arrive centuries after the collapse, but at least it arrives before anything else does, and there is nothing else coming. Here there is no gap, because there is no slower component. The signal and the effect are the same physical thing, moving together. No instrument, no observatory, no funding level, no future technology gets you a single second of notice. There is no messenger traveling ahead of the message. So what are these things? For about 25 years after that first paper, nobody knew, and the argument split into two camps. One said the bursts were relatively nearby, inside our own galaxy. The other said they were at cosmological distances, billions of light years out. The distinction mattered enormously, because the same brightness from 1,000 times further away means an unimaginably larger explosion. The question was settled in two steps. The first was a survey instrument flown on the Compton Gamma Ray Observatory in the 1990s, which catalogued thousands of bursts and mapped where they came from. If they were in our galaxy, they would concentrate along the band of the Milky Way, because that is where our galaxy's stars are. They did not. They were spread evenly across the entire sky, in every direction, with no pattern at all. An even spread in all directions means you are at the center of something, or you are looking at something so far away that our galaxy's structure does not matter. The second option is the one that turned out to be right. The second step came in 1997 from an Italian and Dutch satellite called Bepo-Sax, which could do something the others could not. It could work out a burst's position quickly and accurately enough to tell other telescopes where to look, while there was still something to see. In February of that year it caught one, and follow-up observations found a fading glow at the same spot, and then that glow was traced to a faint, distant galaxy, billions of light years away. Now do the arithmetic on the energy that implies. A typical long gamma-ray burst, if the energy was spread evenly in all directions, would release in a few seconds roughly as much as the Sun will emit over its entire lifetime of about 10 billion years. I want to slow down on that comparison rather than let it slide past, because it is the kind of sentence that stops meaning anything. The Sun has been shining for 4.5 billion years and has about 5 billion left. Everything it will ever radiate, the whole output of a star across the entire history of the Earth and well past its end, released by something else in the time it takes to read this sentence. And now, the honest correction, because that figure is misleading, and the field knows it is. The energy is not spread evenly in all directions. It comes out in two narrow jets, opposite each other, with an opening angle of only a few degrees. That means we only detect the bursts that happen to be aimed near us, and it means the true energy released is smaller than the naive figure by a factor of perhaps 1,000, which still leaves them as the most energetic events in the universe since the beginning of it. But I would rather you have the corrected number and the reason for it than the impressive one. They come in two kinds. The long ones, lasting more than about 2 seconds, come from the collapse of very massive stars, where the core fails and forms a black hole and drives a jet out through the star's own body. The short ones, under 2 seconds, come from two neutron stars merging. We know the second one is right because of that event in August of 2017, where gravitational waves and a short gamma-ray burst arrived from the same place within seconds of each other. Now let me give you the one that came closest to being visible to ordinary people. On the 19th of March, 2008, a burst went off in a galaxy roughly 7.5 billion light-years away. That is more than half the age of the universe. The light left before the Sun existed, before the Earth existed, before any of the atoms in your body had been assembled into anything. For about 30 seconds, it was visible from Earth with the naked eye, not through a telescope. If you had been standing outside, in a dark place, looking at the correct empty patch of the constellation Boötes, at the correct moment, you would have seen a faint star that was not there before and was not there afterward. Nobody was. It was caught by a satellite, and the ground telescopes that swung onto it did so automatically, within seconds, on instructions from software. A thing more than halfway across the observable universe was briefly bright enough to see with a human eye. and the human eyes on the planet were all pointed somewhere else. So the obvious question, could one of these hurt us? The rough figure in the literature is that a long burst would need to be within about 6,000 light-years and pointed close to directly at us to do serious damage, and the damage would not be a blast. At that distance, the gamma rays would not reach the ground. What they would do is chemistry. Gamma rays hitting the upper atmosphere would break apart nitrogen molecules, and the fragments would recombine into nitrogen oxides, and nitrogen oxides destroy ozone catalytically, meaning one molecule can take apart many. Estimates suggest a substantial fraction of the ozone layer could be depleted, and the recovery would take years. The result would be a sharp rise in ultraviolet at the surface, damage to plankton and to the base of food chains, and a serious problem for anything that lives in the top layer of the ocean. Adrian Mellett and Brian Thomas have argued that this may have contributed to the mass extinction at the end of the Ordovician, around 445 million years ago, and pointed at the pattern of which organisms died, surface-dwelling species faring worse than deep-water ones. I want to flag clearly that this is a hypothesis with suggestive circumstantial support, not an established finding. There are competing explanations involving glaciation and sea level change that do not require anything from outside the planet. It is an interesting idea that has not been demonstrated, and you should file it that way. Which brings us to the one object that made people genuinely nervous, and to a scientist correcting his own scary result. In 2000, Peter Tuhill and colleagues used the Keck telescope to image a binary star system about 8,000 light-years away, catalogued as WR104. What they saw was beautiful and strange. A spiral of dust, wound like a pinwheel, produced by the winds of the two stars colliding as they orbited. The spiral appeared almost perfectly circular, and a spiral looks circular when you are looking straight down its axis, which implied that the orbital pole of that system, and therefore the likely direction of any jet it eventually produces, was pointed near us. One of the stars is a Wolf-Rayet star, a type that is a strong candidate to end as exactly the sort of collapse that makes a long burst. That result got a lot of attention, understandably. Then, over the following years, Tuhill's own group kept working on it, and in 2018 published spectroscopic measurements of how the material was actually moving. Motion tells you geometry in a way that a projected image cannot. The result was that the system is inclined by something like 30 to 40 degrees from face on. Not pointed at us. Probably not pointed at us at all. I like that story more than any of the alarming ones, and it is worth being explicit about why. The frightening result and the reassuring correction came from the same person, following the same method, over 18 years. Nobody was embarrassed. That is the process working exactly as intended, and it is the reason to trust any of the other numbers in this video. But now let me close the stage honestly, because there is one exception to the zero warning claim, and it deserves to be here. For a nearby core collapse supernova, not a burst, the universe does give you a few hours. When the core of a massive star collapses, it emits an enormous pulse of neutrinos, and neutrinos barely interact with anything, so they leave the star immediately. The light has to fight its way out through the star's outer layers, which takes hours. We have seen this exactly once. On the 23rd of February, 1987, a star exploded in a satellite galaxy of the Milky Way, and detectors in Japan, the United States and Russia each recorded a brief burst of neutrinos. The optical brightening was noticed about 3 hours later. There is now a standing international network built on that lesson, whose only job is to cross-check neutrino detectors and issue an alert if several see the same pulse at once. So there is a warning system for a nearby supernova, and it works. And it would give astronomers a few hours to point everything at the right patch of sky. It would give you nothing at all. It is a warning built for telescopes, not for people. There is no action attached to it. That is stage 6. The gap between the news and the event has now closed completely, and for the first time, it has closed for reasons that no future civilization could engineer around. Now we go somewhere stranger, where nothing explodes, nothing hits us, nothing threatens anybody, and things are being lost permanently at a rate of a few per second, and you can watch it happening tonight. In the first years of the 20th century, the Harvard College Observatory employed a group of women to measure photographic plates. They were called computers, because that is what the word meant then. It described a person who computes. They worked long days examining glass plates of the night sky, comparing exposures, measuring the brightness and position of stars by eye and by hand, and recording numbers in ledgers. They were paid around 30 cents an hour, less than the men doing comparable work, and they were generally not permitted to direct their own research. One of them was Henrietta Swan Leavitt. She had been assigned a specific and tedious job: catalogue variable stars, stars that brighten and fade, on plates of the Magellanic Clouds. That assignment turned out to matter enormously, for a reason nobody anticipated. The Magellanic Clouds are separate small galaxies, so every star in them sits at roughly the same distance from us. Any difference in apparent brightness between two of those stars is a real difference in their output, not an artifact of one being nearer. Leavitt worked through more than 1,000 of them, and in 1912 she published a result of 4 pages. For one particular type of variable star, the ones we now call Cepheids, the brighter the star, the longer its cycle of brightening and fading. The relationship was clean, and it ran in a straight line. Now think about what that gives you. Measure how long a Cepheid takes to complete a cycle, which is easy, because it only requires patience and a clock. From the cycle you know its true brightness. Compare that to how bright it looks, and since brightness falls off with distance in a way we understand exactly, you get the distance. Before Leavitt, we could measure distances to nearby stars by parallax and essentially nothing beyond that. After Leavitt, anywhere we could find a Cepheid was measurable. She was not allowed to follow it up. The observatory director assigned her back to other work. She died of cancer in 1921 at 53. In 1925, a Swedish mathematician wrote to Harvard intending to nominate her for the Nobel Prize, and had to be told she had been dead for 4 years. Everything in the rest of this stage was built on those 4 pages, and I want you to hold on to her for the next few minutes, because everything that follows is going to get very large and very cold, and it is worth remembering that the tool for measuring the size of the universe was made by one woman at a desk, counting the same stars over and over, on work she did not choose and was not allowed to follow up. Every distance you are about to hear traces back to that. Every number about how far away anything is, out to the edge of what we can see, sits on a chain of measurements whose first link is a person comparing photographic plates by eye for 30 cents an hour. Because in 1923, Edwin Hubble found a Cepheid in the Andromeda Nebula, applied Leavitt's relation, and found it was far outside our own galaxy. Andromeda was not a cloud of gas in the Milky Way. It was another galaxy, entire, and the universe was suddenly enormously larger than anyone had been arguing about. And by 1929, he had the second result, the one that opens this stage properly. The further away a galaxy is, the faster it is receding from us, and the relationship is proportional. The universe is expanding. This is the 7th stage, and it is the only one tonight where nothing is coming toward us at all. Nothing here threatens you. And it is, I think, the bleakest thing in the video. First, let me clear up what expansion actually is, because the usual picture gets it wrong in a way that matters. The galaxies are not flying apart through space, like debris from an explosion, into some pre-existing emptiness. Space itself is expanding, everywhere, all at once. Every region of space is getting larger, and galaxies are carried along with it, like markings on a rubber sheet being stretched. The consequence is strange, and it is worth stating plainly. Because every stretch of space between here and a distant galaxy is expanding, the further away something is, the more expanding space lies between us, and the faster it recedes. Beyond a certain distance, the total adds up to a recession speed greater than the speed of light. That is allowed. Nothing is moving through space faster than light. Nobody is breaking any rule. The space in between is simply being added faster than light can cross it, and there is no limit on how fast space can grow. Then, in 1998, two competing teams made the same measurement and got the same unwelcome answer. Both were using exploding stars of a particular kind, the ones that go off with a consistent and predictable brightness, which makes them usable as distance markers much further out than any Cepheid. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. They were rivals, and they were both trying to measure how much the expansion of the universe was slowing down. Everybody assumed it was slowing. Gravity pulls. The universe is full of matter. The only question was whether there was enough matter to eventually halt the expansion and reverse it. The distant supernovae came back fainter than expected, which meant that the expansion had been slower in the past than it is now. It is not slowing, it is speeding up. Both teams checked for errors for months, because neither wanted to publish that. Both published anyway, and you should register how unusual that is, because it is the thing that ought to make you trust the result. Two competing groups, racing each other, each with every incentive to find the other's mistake, arrived independently at a conclusion that neither of them wanted and that made their own field considerably more confusing. If you are ever wondering whether to believe a scientific claim, that is the shape to look for. Not a result that confirms what the people who found it were hoping for, a result they spent months trying to make go away. They shared the Nobel Prize in 2011, and we still do not know what is causing it. We call it dark energy, which is a label for the size of our ignorance rather than an explanation of anything. Now here is what acceleration does, and this is the payload of the stage. There are two different boundaries around you, and they are constantly confused, so let me separate them, because if you take one thing from this stage, it should be the difference between them. The first is how far you can see. Light has been traveling toward us for about 13.8 billion years. And because space expanded while it was in transit, the objects that emitted the oldest light we receive are now around 46 billion light-years away. That is the edge of the observable universe. It grows over time, because more light keeps arriving. The second boundary is different, and it is the one that matters. It is the distance beyond which light leaving a galaxy right now will never reach us. Not in 1 billion years. Not in 100 billion, never in infinite time, because the space in between is growing faster than the light can cross it. That boundary sits at roughly 16 billion light years. And now put the two facts side by side, because this is the whole stage in two lines. You can see out to about 46 billion light years. Anything beyond about 16 billion light years is already permanently out of contact with you. Which means the night sky is full of galaxies whose light we are receiving right now, tonight, that we are permanently severed from. We are watching light they emitted long ago, while it could still make the crossing. Everything they have done since, and everything they will ever do, is information that will never arrive here, no matter how long anyone waits or how good the instruments get. Nothing has happened to them. They are perfectly fine. There are presumably stars forming in them tonight. And if there is anybody there, they are having an ordinary evening. But the relationship is over. The causal connection between us and them was severed at some point in the past, and the sky simply has not caught up, and will keep showing them to us for a very long time while they drift further out of reach. That is what this video's title means in its most literal form. Not that they died, that from where you sit they are already gone, and you are looking at a picture of somebody who left. And it keeps happening. Galaxies are crossing that boundary continuously, right now, as you listen. Estimates suggest that of the roughly 2 trillion galaxies in the observable universe, only a small percentage remain reachable even in principle by something traveling at the speed of light starting today. The rest have already gone. I would treat that percentage as an order of magnitude rather than a precise figure, because it depends on the dark energy model, but the direction is not in doubt, and the number only goes down. Now let me take it to the end, because there is a version of this that I find genuinely difficult, and it was worked out properly by Lawrence Krauss and Robert Scherer in 2007. Run the expansion forward. The Milky Way and Andromeda are gravitationally bound to each other and to a few dozen smaller galaxies in what we call the local group. Gravity there is winning against expansion, so the local group stays together. That is worth dwelling on for a moment, because it is the one piece of good news in this stage. Expansion does not pull apart things that are held together. It does not stretch atoms or planets or solar systems or galaxies, or even clusters of galaxies where gravity is strong enough. The Earth is not slowly growing. Your body is not being stretched. Expansion only wins in the enormous empty regions between bound structures, where there is nothing holding anything to anything. So the local group survives, and Andromeda is currently approaching us at about 250,000 miles an hour, because on that scale gravity is comfortably beating expansion. In roughly 4 to 5 billion years, the two galaxies pass through each other. Almost nothing collides, because the distances between stars are so vast that two galaxies can occupy the same space and leave individual stars untouched. What happens instead is that the gravitational disturbance throws stars onto new orbits, triggers a burst of star formation from the compressed gas, and after a few passes the two spirals settle into a single large elliptical galaxy with no clear structure. The Sun will probably still exist for the early part of that, though it will be entering its own difficulties by then. The night sky, for anyone here to see it, would be extraordinary for a few 100 million years, and then everything else goes away. Every other galaxy in the universe recedes, redshifts, dims, and eventually its light is stretched so far that it becomes undetectable by any instrument. Over roughly 100 billion years, one by one, they leave. The faint background glow left over from the Big Bang, which is our single most important piece of evidence about the early universe, stretches too, until its wavelength is longer than any detector could plausibly capture. So put yourself on some planet, 100 billion years from now, doing good science with excellent instruments, better instruments than ours. You are careful, you are honest, and you are not missing anything that is there to be found. You see one galaxy, your own, sitting in an empty, static, unchanging void with no other objects at any distance in any direction, no background radiation, and no redshift to measure because there is nothing left to measure it on. You would conclude, correctly by every piece of evidence available to you, that you live in a single island of stars in an eternal and unchanging universe. And you would be wrong, and there would be no way for you to find out, and nothing you did wrong would explain it. That was the standard picture on Earth in about 1910. It was wrong then too, and we only found out because we happened to be alive during the window when the evidence was still visible. The evidence expires. That is the thing that gets me. Not that the universe ends, but that the record of what it was gets quietly deleted, while it stays perfectly possible to do rigorous, careful, honest science and arrive at a confident and completely false picture. We are not living at the beginning of the age of astronomy. We may well be living near the end of the only period in which the important facts were still available to be found. That is stage 7. Nothing threatened you. Things are simply becoming permanently unreachable, on a schedule, and they continue to appear in the sky long after the connection is gone. Now, one more stage, and this is the one where the event and the news are not merely the same speed, but literally the same object, and where the phrase "already happened" stops being a figure of speech. In 1980, two theoretical physicists at Harvard published a paper with an unremarkable title about gravitational effects on vacuum decay. One of them was Sidney Coleman, who was among the most respected theorists of his generation, and also one of the funniest, which is a rarer combination in that field than you might hope. The paper is technical and mostly unreadable without the training, but there is a passage in it, written in plain language, that has been quoted ever since, and the reason it gets quoted is that Coleman describes something appalling in a tone of complete calm. He is describing what happens if empty space turns out not to be empty in the way we assume, and he notes that anyone present would not have time to be upset about it, because the transition would arrive at the speed of light, And then he adds, dryly, that inside the new region not only would life as we know it be impossible, so would chemistry as we know it. This is the 8th and final stage, and the warning time is 0 as a matter of law. I need to build up to why, because this one requires an idea that is genuinely unfamiliar, and I want you to actually have it rather than just hear the scary conclusion. Start with what a vacuum is. In everyday language, a vacuum is nothing. Take a box, remove all the matter, and what remains is empty. In modern physics, that is not what remains. What remains is a set of fields that fill all of space and cannot be removed, sitting in their lowest energy configuration. The vacuum is not the absence of things. It is the quietest possible state of the things that are always there. One of those fields is the Higgs field. It has a value everywhere in space, and that value is not 0, and that fact is why particles have mass. If the Higgs field's value were different, the mass of the electron would be different, and if the mass of the electron were different, then the size of atoms would be different, and chemistry would not work the way it works. So here is the question that 1980 paper was about. Is the value the Higgs field currently has the actual lowest one available? Or is it merely a low one, with something lower elsewhere that it has not found? Picture a ball resting in a shallow dip partway down a long hillside. If you walked up and nudged it, it would roll back to the bottom of its dip. Leave it alone and it will sit there indefinitely. As far as you can tell from standing next to it, it is at rest and it is staying there. But it is not at the bottom of the hill. There is a lip on the downhill side of the dip, and beyond that lip the ground falls away much further, and you cannot see that from where the ball is sitting. In the physics you were taught at school, a ball in that dip stays there forever unless something gives it enough of a shove to get over the lip. Quantum mechanics does not work that way. A quantum system in a dip like that has a probability, small but not 0, of simply appearing on the other side of the barrier without ever going over it. This is called tunneling, and it is not speculative. It is the mechanism by which the sun works and by which certain radioactive nuclei decay, and it has been measured to high precision for a century. So if our vacuum is a dip rather than the true bottom, then somewhere, eventually, a small region of space tunnels through. And what forms there is a bubble. Inside that bubble, the Higgs field sits at its true lowest value, whatever that is. The physics inside is different. The masses are different. Atoms as we have them do not hold together. And the bubble does not sit still. The interior is at lower energy than the exterior, and that energy difference drives the wall outward, and the wall accelerates until it is traveling at essentially the speed of light. Now put that together with everything we have built tonight. The wall travels at the speed of light. Light is the fastest signal there is. Therefore, the first information you could possibly receive about the wall's existence arrives at exactly the same instant as the wall. There is no gap. There is not even the possibility of a gap. In stage 6, the gamma rays and the burst arrived together because they were the same photons. Here it is even more complete than that. There is nothing to detect. A gamma ray burst at least emits something you could measure if you happen to be pointed the right way. An advancing vacuum wall emits nothing ahead of itself because nothing can get ahead of it. The sky would look completely normal. Every star in its place, every measurement you could take returning exactly the expected value. And then the transition would sweep across the earth in a fraction of the time it takes a nerve impulse to travel from your hand to your brain. Not painful, not frightening. There is no interval in which to have an experience. So why does anybody take this seriously at all, rather than filing it as a thought experiment? Because of a measurement made in 2012. That was the year the Higgs boson was confirmed at the Large Hadron Collider, and with it came the field's mass, at around 125 giga-electronvolts. That number, combined with the mass of the top quark, feeds into a calculation about the shape of the hill. And when you run the equations up to extremely high energies, the answer that comes back is that we appear to be sitting in a dip rather than at the bottom. The technical word is metastable. Stable for a very long time, but not permanently. Now I want to spend real time on the caveats, because this is exactly the kind of result that gets reported as though it was settled, and it is not. And the reasons it is not are specific. First, the answer is extremely sensitive to the mass of the top quark. That mass is known to about 0.5%, which sounds precise and is not precise enough. Shift it slightly one way, and we are comfortably stable. Shift it slightly the other, and the picture changes. We are sitting close enough to the boundary that our measurement uncertainty straddles it. Second, the calculation assumes there is no new physics at any energy between the ones we have tested and the scale where gravity becomes a quantum problem. That is an enormous assumption, and almost nobody believes it is actually true. Any new particle in that vast unexplored range could change the shape of the hill entirely. Third, and most importantly, the timescale. The estimates for how long we would expect to wait for a tunneling event are numbers like 10 to the power of 100 years, and many published figures are vastly longer than that. The universe is about 10 to the power of 10 years old. That is not a close call. That is a probability so small that calling it negligible is generous. And there is a straightforward empirical argument that I find more convincing than any of the calculations. It has not happened yet. Not here, and not anywhere in the observable universe in 13.8 billion years, across a volume containing something like 2 trillion galaxies, including environments far more extreme than anything we could ever produce. Neutron-star collisions, black hole mergers, cosmic rays hitting each other at energies far beyond the Large Hadron Collider, constantly, everywhere, for the entire history of the universe. If the vacuum were easy to tip, it would have tipped. So if it is that unlikely, why is it in the physics literature at all, rather than in a novel? Because the calculation is not really about the end of the world. It is a diagnostic. When theorists run the stability of the vacuum out to very high energies, what they are actually testing is whether the standard model of particle physics can be the whole story. If you assume it is complete, and you turn the handle, you get an answer that sits uncomfortably close to a boundary. That closeness is a clue. It is the kind of result that suggests something is missing, in the same way that a bridge calculation coming out at exactly the load limit suggests you have left a term out. There is also a direct connection to the early universe. The leading account of the first fraction of a second after the Big Bang involves a field sitting in a high-energy state and then rolling down to a lower one, releasing an enormous amount of energy in the process and driving a period of extremely rapid expansion. That is the same class of physics. So false vacuum transitions are not an exotic add-on. They are close to the center of how we think the universe got its structure, and one of them may well have already happened right at the beginning and produced everything, which is a much better reason to study it than the apocalypse, and it is why the topic gets serious attention from people who would never describe themselves as worried. But there is one last connection to make, and it is the reason this stage sits where it does rather than anywhere else in the video. Suppose a bubble did nucleate, somewhere out there, some time ago. Where could it be, and could it reach us? The answer is the 7th stage. A bubble expanding at the speed of light is, from our point of view, exactly like a photon. It obeys the same rules about what can reach us, and we established that anything beyond about 16 billion light-years is already permanently out of contact, because the space in between is expanding faster than light can cross it, which means the accelerating expansion of the universe, the thing that in stage 7 was quietly deleting the sky and stranding every galaxy beyond our reach, is also the thing protecting us. The overwhelming majority of the universe cannot send us a vacuum bubble, for precisely the same reason it cannot send us a radio signal, or a photograph, or a hello. Dark energy is taking the universe away from us. It is also holding the door. That is the 8th stage, and that is the last of them. Now I want to stop and change register completely, and do the thing I think this subject requires, because I've just spent a long time walking you down a ladder of decreasing warning times, and if I leave it there, I have given you an inaccurate picture of the world, and an inaccurate picture is not what this channel is for. So let's go back through all 8 and ask the question I have deliberately been holding back. Not how much warning would you get, how likely is any of it? Let's go back through all 8, in order, and I will give you the honest probability rather than the interesting one. The sun disappearing was a thought experiment and nothing more. There is no mechanism in physics that permits it. I used it because it is the cleanest possible illustration of the 8-minute delay, and for no other reason. The probability is not small. It is 0. Betelgeuse will explode, and it will not hurt you. The distance is more than 10 times the threshold where a supernova starts to matter for a planet, and the most likely outcome for anybody alive when it happens is the best free show in recorded history. If there is anything to regret about Betelgeuse, it is that the odds of it going off during your particular lifetime are poor. The waiting time is measured in tens of thousands of years, and you have a few decades. A solar storm is the one that will actually happen. I want to be quite direct about that because it is the least exciting thing in this video, and it is the item that deserves your attention. The Sun produces Carrington-class events on a regular basis. We know this because we have watched several of them launch and miss. One study of the historical record put the probability of a direct hit at somewhere around 12% per century, and while that specific figure has been argued over in both directions, nobody in the field thinks the number is negligible. This century, not in 100 million years, not in 10 to the power of 100 years. And the consequences would be genuinely serious, because the vulnerability is not the storm, it is us. We have built a civilization on a grid of long conductors and custom-built transformers, and we did it in a period of relatively quiet solar behavior, and we have never tested it against the thing the sun does routinely. The good news, and it is real, is that this is the most tractable item on the entire list. We have a spacecraft parked upstream specifically to see it coming. We have procedures. Grid operators know what to do. Hardening a network against induced currents is an engineering problem with known solutions, and the main obstacle is that it costs money to prepare for something that has not happened recently. An asteroid impact is the second real one, and here the honest picture is more encouraging than most people expect. For the genuinely civilization-ending sizes, above about half a mile across, we have found the large majority of them, and none are on a collision course for any date anybody needs to think about. That is a solved problem, and it was solved by people doing patient survey work for decades. For the city-sized objects, the ones in the range of a few hundred feet, we have found perhaps 40%, and the average interval between impacts of that scale is measured in thousands of years. So the annual probability is small, and it is not 0, and unlike almost everything else tonight, there is a specific thing being done about it. A dedicated infrared telescope designed to look into the blind spot, and a demonstrated ability to move an asteroid by hitting it. Chelyabinsk-sized events, the window breakers, happen on the order of once every several decades. That one is not a civilizational risk. It is a bad day for one city. The interstellar objects are not a threat at all. Not a small threat, not a threat. They are moving fast and there are not many of them and space is overwhelmingly empty. I included Oumuamua because it is the cleanest example of our detection latency, not because it was dangerous. Nothing about it was ever dangerous. Gamma-ray bursts are rare in a way that is hard to convey. The estimates for how often one goes off close enough and pointed well enough to significantly damage our atmosphere come out at something like once in several 100 million years. That is a real number, and it is not 0, which is why it appears in serious discussions of mass extinctions. It is also not a planning horizon for anybody or anything. The cosmic horizon is certain, ongoing, and completely harmless to you. Galaxies are receding out of reach as you listen, and this will have precisely no effect on your life, your species, or your planet. What is being lost is knowledge, on a timescale of tens of billions of years. It is the only item tonight that is definitely happening, and definitely does not matter to anybody now living. And vacuum decay is, by an enormous margin, the least likely thing in this video. The timescales are so long that they are not really timescales. Every calculation could be wrong, and it would still not be worth a moment of your concern. So here is the honest ranking of everything we have covered, by how much it should actually occupy you. Solar storm. then asteroid, then a very large gap, then everything else. And notice something about the top two. They are the two with the most warning, the two we understand best, and the two we are actively working on. The list, sorted by how frightening it sounds, is almost exactly the reverse of the list sorted by how much it matters. That is not a coincidence, and it is worth naming. The things that make good stories are the ones that are unfamiliar and absolute. The things that pose real risk are usually familiar and partial, and they are boring, and boring is why they do not get funded. So if the danger was never really the point, what was? This is the part I actually wanted to get to, and it is stranger than any of the 8. In 1905, Albert Einstein published a result that is usually skipped over in favor of the more famous ones. And I think it is the most disorienting thing in physics that ordinary people never get told. He showed that simultaneity is not a fact about the universe, it is a fact about your point of view. Take two events that happen at a distance from each other. You measure them and find they happened at the same moment. Somebody moving relative to you measures the same two events and finds that one happened before the other. A third person, moving differently, finds the opposite order. None of you is wrong. There is no experiment that could settle it, because there is nothing to settle. There is no universal clock ticking through the cosmos, defining a present moment that everything shares. Which means the question I opened this video with, where is the sun right now, is not a question with a hidden answer that our instruments are too slow to reach. It is a question that does not have an answer. The phrase "right now on Betelgeuse" sounds like it refers to something. It sounds like there is a fact about the state of that star at this instant, and we are simply waiting 640 years for the news. But the instant those words describe is not a thing the universe recognizes. Now is a local word. It works fine in this room. Stretch it across 640 light years, and it stops meaning anything at all. And the everyday version of this is the part I would most like you to keep. You have never experienced the present moment. Not once. Not even your own. Look at someone across a table. The light leaving their face takes a few billionths of a second to reach your eye, which is nothing. But their voice takes several milliseconds to cross the air. Your retina takes time to convert light into signal. The signal takes time to travel your optic nerve. And your brain takes something like 1/10 of a second to assemble all of it, from different senses running at different speeds, into the single smooth experience of a person sitting across from you talking. Your brain handles that by predicting and by quietly discarding the mismatch, and it does the job so well that you have never noticed. Everything you have ever experienced is a reconstruction of something that already finished happening. The sky is doing the same thing to you on a scale of centuries, and your own nervous system is doing it on a scale of milliseconds, and there is no difference in principle between the two. You are always looking at the past. You always have been. The sky just makes it obvious enough to measure. Let's pull every thread we've followed tonight together, and the cleanest way to do it is by the one number we have been tracking the whole way down. How much warning? On the scale of 8 minutes and 20 seconds, the sun, the nearest star, the one we understand better than any object in the universe, and even it is a historical document. The light on your face left a core that released it while our species was still learning to make tools. On the scale of centuries, Betelgeuse, 640 years of transit, which means everything that has happened to that star since Chaucer is still on its way, and the sentence, "it may have already exploded," is not dramatic license. It is a plain description of what we do not and cannot know. On the scale of an hour, a solar storm, the only item tonight where the danger travels slower than the news, and the only reason we have any ability to respond at all. And even there, the useful part of the warning turns out to be the last 15 minutes, when a spacecraft 1,000,000 miles upstream finally measures which way the magnetic field is pointing. On the scale of minutes, a rock out of the sun, Chelyabinsk, where the flash arrived instantly and the shockwave took 3 minutes, and an entire city spent those 3 minutes walking toward their windows. On the scale of negative days, Oumuamua. Closest approach on the 14th of October. Discovery on the 19th. A visitor from another star came, passed and left, and we found out on the way out. On the scale of 0, a gamma ray burst, where the signal and the event are the same photons, and no telescope ever built or ever conceivable buys you a single second. On the scale of already gone, the galaxies passed our horizon. Still in the sky, still bright, still being photographed, and permanently severed from us by expanding space that light cannot cross. And on the scale of 0 by law, the vacuum, where the wall and the news are the same object, and where the accelerating expansion that is taking the universe away from us is also the thing that keeps almost all of it from ever reaching us. 8 stages, and the number went from 8 minutes to nothing, and then past nothing. So here is the honest bottom line, and it is simple and a little humbling. You are not in danger from most of this. The 2 items that could plausibly affect your life are a solar storm and an asteroid, and both are being worked on by people who understand them. And both have real defenses that get better every year. Everything else on the list is either impossible, harmless, or so rare that including it in your worries would be a mistake. What you are is late. Permanently, structurally, unavoidably late to everything you have ever seen. And there is one last thing, which is the only item in this entire video that has definitely already started, that is definitely irreversible, and that nobody is going to stop. The sun is getting brighter. Not violently, not in a way anybody will notice. As hydrogen fuses to helium in the core slowly contracts and heats, and the star's output creeps upward by around 1% every 100 million years. It has been doing this since it formed. The sun that warmed the dinosaurs was measurably fainter than the one outside your window. Run that forward, and it eventually breaks the mechanism that keeps this planet habitable. As the sun brightens, the weathering of rock speeds up, and that process pulls carbon dioxide out of the air. Below a certain concentration, plants cannot photosynthesize. That is the flaw, and it arrives long before the oceans boil. The estimates for when complex life becomes impossible here run from roughly 600 million years to about 1 billion, and the error bars on that are wide, and I would rather give you the range than pretend at precision. But notice what kind of item that is. It is not a possibility. It is not a risk with a probability attached. It started 4.5 billion years ago. It has been running continuously through every moment of the history of life on this planet, and it is running right now, tonight, while you listen to this. The clock did not start when we noticed it. Every single thing in this video was already in motion before anybody looked up, and the looking up changed nothing except what we know. So the next time you go outside on a clear night and look at that sky, try to hold 2 things at once. The first is that you are not looking at a place. You are looking at a stack of moments, each one arriving from a different depth in the past, assembled into a single picture by the accident of where you happen to be standing. And the second is that this is the ordinary condition of everything. The stars are just far enough away that you can measure it. There is no view of the universe as it is. There never was. There is only the light that has arrived so far. Thank you for joining me tonight on this trip out through the delayed sky. If you found this as fascinating as I did, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making these deep dives into the cosmos. Go outside tomorrow, in the afternoon, and stand in the sunlight for a moment. It took 100,000 years to get out of the core, and 8 minutes to cross the gap, and it is falling on your face tonight. It is the oldest thing that will ever touch you, and it arrives, on time, every single